Hi everybody. Is the mic on? All right, cool. All right. All right, I get started. Yeah, so subtle pitfalls in C and C++ programming, like Windows version edition. Um, so a little bit about myself. I've been like working at IOActive as Senior Security Consultant since 2024. My area of interests are mostly vulnerability research, binary exploit development, OS internal, everything low level. The stack of technology basically is C, C++, and assembly. Still in the software sphere, nothing hardware yet. Currently I'm building a software tool for Windows, security tool. He used like an EDR-like architecture, and we're gonna discuss that in a bit. Concerning the presentation, I like to interact, with the audience. So we will be asking questions. As raise your hand if you did that or that. But where I prefer to keep like the real questions at the end for the Q&A. You can see my website there. Sometimes I write blog posts, and this is my GitHub. Yeah, so that's about it. Oh, yeah, one more thing. I'm delighted to share with you that I recently, just today, become like a British citizen this morning. So yeah, I'm so pleased. Thank you guys. Thank you. Without anybody. I did sing that. I did. So yeah, this is the agenda basically. We have a lot to cover. So we gonna scope the talk, and then we gonna have like the main difference between the languages C and C++, how we handle strings and object life, time thing, synchronization, calling convention, and some compiler behavior. That's a very interesting one. We have a conclusion, and then finally Q&A. All right, let's dive in. So in this talk, basically it's kind of like a storytelling of me producing bugs and how I fix them while writing the security tool that we will discuss in a minute. Most of these bugs are not necessarily security risk. They don't have like security risk in sense, like directly, but they can like turn into security a problem. I will be referencing a lot of like Windows internals, hence why I added like the Windows edition in the title. We're gonna cover like loads of assembly code as well, right? Only like 32 bits and 64. ARM is out of scope for this one. And we might talk about like an interesting behavior in a compiler. We might or might not find like an optimization bug with the Microsoft compiler, C++ compiler. Now that's the like architecture that I'm using for the project. So I have like a kernel that injects DLL into new created processes. Basically, the DLL agent is in 32 bits, 64 bits. I support both of them. But the thing that we should be aware of for context is like I inject the agent like super early, and that can create loads of issues, and the environment change from like the user land perspective. So we will tackle some code like both in the kernel side and the user land side. Right. Now, as I mentioned like in this previous like slide, we have like a DLL that we inject. DLL itself, like it's, I would say, quite complex in sense. It depends on how you use it. But the restriction that we have right now is like the DLL main function. If you not like treat it properly and respect the restrictions there, you can reach like deadlock. We're gonna discuss that in a minute as well. So there is loads of things that we're gonna discuss, including like the Windows loader. So is one of the restriction that we had encountered in that one. So the constraints is like really the agents, like, in security tools, right, EDR or antiviruses, they do loads of hooking, right? So they inject a DLL into a process, and they try to keep the DLL itself super lean. Super lean for many reasons, optimization, keep it like simple so they can audit that here and but there is also some restrictions as well. So basically, if you're a security product, you want to like inject at early stage of the creation of a process. And when you do that, so obviously either you inject after the NTDLL gets loaded or kernel 32. In both cases, well, the NTDLL one would be the most kind of like used, but if you want more freedom, you can like inject after kernel 32, so you can have like access to certain APIs. Now, when you're using the DLL, you know, C++ has like, by default, like, you know, exceptions. We need to disable the exceptions, in sense like from the C++ perspective there, because it creates loads of issues. For instance, if you run, there is a code that runs into the DLL, and you're hooking like very sensitive like API, you can lead into, you know, a deadlock, because like the loader was doing something and you accidentally called a heap. Now, in this kind of like environment and stuff like that, we try to avoid like heap allocations. We mostly use kind of minimalistic usage of heap, so we will focus on the stack. And we're gonna look at that in a bit more details. But before we do that, let's discuss like the difference between C and C++ languages. Raise your hand if you prefer C. All right, cool. We have a bench. All right, that's quite a good number. Who prefers C++? I don't. All right. Yeah, fair enough. Right. So in this context, C is kind of like more suited for this kind of work. The reason for that is like very lean, minimal. Yes, of course, he only got like some procedural. It's procedural language. You can do some like OPP in that, or kind of mimic it per se. You can do stuff, but you're limited. You don't have lots of features, but you can do loads of stuff. And the abstraction is very low to none, I would say. And that's the interesting part that we're gonna say. Is less strict from type-wise. Everything is considered as an int. Now, if you go to C++, it's very rich. It's a beast as a language. There is loads of things. He supports loads of like paradigms. I don't know. Can I use like functional kind of type of programming? OPP, obviously. You know, template programming here and there. And the level of abstraction is super high. So sometimes you run something, you don't know what exactly going under the hood, right? It's very rich, strong type in sense, I would say per se, because it's still kind of lacking in sense, but still. So that's the main kind of like difference between these two languages. In this talk, we're not gonna cover like templates and stuff. We're gonna just keep it very minimum for like the context of like writing security tools at that level. We're gonna start with the fundamentals, right? So when we start programming, we need to know how to initialize a variable and stuff like that. C is very simple. There is a specific way to do that, and it works as you can see it. It's mostly plain. Like in C++, there is several kind of forms, and it supports several things. You don't have only variables, you have also objects. The objects change everything in that context. So you can go to the documentation, you can see loads of like information on the initialization perspective, and we're gonna see the forms and the models used in C++ that could like trick you at some point. So we have like very simple foo bar structure here, right? So far it's both one, it's very plain, there's nothing, right? Long ID and a char like, you know, 2.6, yeah. A buffer, but it's aligned for like 64 bits, right? Like so far. Now we have several kind of type of initialization in C++. Look, I mean, 1, 2, 3, 4, 5, kind of like 3 of them, kind of sort of thing, but I'm not listing them all, but it's gonna be, so the default initialization is something that we're gonna cover, like several types, and we need to understand like type of like objects as well, but we're gonna focus on the one that uses braces, right? Like curly braces as initialization. This is the one that we're gonna focus on, as it's used like in the industry a lot, and there is a reason for that. And we will see that in a minute. Now, a funny thing is, like, I'm not like trying to make a war, like declare a war here or something like that with my C++ friends over there. Um, you know, in C we had like, you know, the let's not go there. But like just in the C++ 2020, we just have like this kind of like type of initialization that we're gonna discuss in a minute. And it makes some problems. But the C++ default initialization here, this is how it works under the hood, right? Now, we have that class that we were discussing, right? That foobar thing, right? Simple data, nothing special so far. And we're using the return byte. So we have like 3 plus something in the buffer and the index 0. So what would be the result of that from your side? So we have 3 plus something in the buffer. We don't know where is it as index 0. What could it be? Who says 3? Raise your hand if you think it's 3. Right. Who says something else? Right. Let's have a look now at the. So basically, oh, hold on a second. It's supposed to be. So let's tackle this one. So we have a 3 plus a buffer of like at index 0. So we don't know what's gonna happen there. In sense, we have a 3 plus something random. It's not initialized. It could be any value at all. It depends on the compiler. So we don't know what's the outcome from that. Now, in order to try this, let's see if we put like this initialization type, default initialization, and we use like 41, which is, I guess, 65 as a decimal value. And let's do that again. So what would be the outcome for this one? Also, if you notice something very interesting here, we didn't have in the previous one, with the buffer, we didn't initialize it. In the assembly code, right, there is nothing there in sense. Look at the blue code. That's the reflection. So we can see that we move like EAX and use like the n sign, like multiply things. It's gonna be like 0 there anyway. And then we're gonna see the value it gets there. It adds 3, but something in that variable, we don't know why is it, is gonna reproduce undefined value. Now, if we go here though, we see something like different. We're in C++. I just initialized something, I used that 41 hex. And we see something very interesting. Like, you know, can you see the instructions in green? Right? So we see a constructor call, but we can't see that like in the code, right? This is something, that's what the abstraction can make. So there is abstraction that C++ does things that we don't know. So basically, he's trying to initialize. He gets the value from buffer, and then commute it. And so if we go back here, do you see? All right. All right. I kind of like changed the variable of optimization here, so you can have a look at that. So in the first slide, I didn't put like the optimization thing. So I enabled optimization so we can see what's going on under the hood. Because if you go back, right? Sorry. If you go back here, we see that we have a call to a constructor is called, but we don't know what's going on under the hood, right? But if we go back here and enable the optimization thing, we don't see the constructor call, but we can see what's going on under the hood. We can see like the 41, which is like here, like the 64 here, 65 here, and we see what's going on. So we can predict with that code, we can predict the output of main, the return value of main. So what would be well, let's say it's gonna be 68. And the reason for that, as you can see like in the previous code, is we initialized as the first index with the 65 value. We can try this out, but let's not like try it now. Let's keep it at the end. But let's move to another example to illustrate the idea. So we have this structure now as well, but this one is different. It's no longer a plane, a pod structure. We have a constructor, and we have two initialization though. So we initialize this one in the red, and the other one in the orange. So the orange is a constructor without any parameter. So who can guess what could be like the value? We had like 69 this time, not 68. And the reason for that is we overrided the way C++, the priority, or the order of like initialization is, the first thing that he looks up for, like when using default initialization, is the constructor without any parameters. So that's the one that gets run first. So, but in the assembly code though, the instruction, the one that gets generated, is the initialization of the buffer. So if you can look at the one here, we can see the 41, which is optimized and then get called afterwards around down here. Trying to find the slide. Okay, so the takeaway from this one is that the default initialization, which is this form, right? We don't give a value, a sanitization syntax to that. The behavior is to look at the default constructor. If it's not there, it sees if there is any member of the struct initialized. If it does, it uses that as a value. Now, if we go back to the other like curly brace initialization aspect of that, they have like different names, and you know, like you can see like the copy list initialization. Everyone has its own kind of behavior. Now, aggregate, just to be precise, when we see aggregate initialization here, an aggregate type in C++ is an object that doesn't have necessarily, it's not like a pod necessarily, it could be, but it's not necessarily a pod. It's any object that doesn't have like static members, variables there, or doesn't call any like constructor, right? Or the constructor in that regards. So going back to the element that I was saying about like C and C++, so there is this element of designated like initialization. This is something like kind of recent in C++ 20, but in C has been kind of like been there like for quite a while. And the funny aspect of nuance on the initialization perspective from that one is like the order matters in C++. So if you have like even using the name of the field, if you're not putting them in a specific order, it's not gonna compile. Where in C you can have like in different order and it still works just fine in that regards. So that's the first mistake that I have made coming from C to C++, is I wanted to initialize something to 0, right? That's the best practice to avoid like any issues there. So and C++ has this this type of like syntax to initialize the value to 0. Now this is a good syntax. I mean, it's used like widely in the industry, and there is a meaning behind that. It's not just like a random kind of like syntax. It's kind of, you cannot have like a narrowing problem for conversion. If you have like, for instance, like a variable, you know, float things, and you declare it as a long, and you kind of use like this as a value, it won't kind of compile with it. No, it cannot compile that. That's not the same type. This is quite neat, and also it's uniform. So you can, when you look at it, you understand exactly what's going on there, because like if you have nested like object, like in this is like a snippet from like the WebKit project. It uses this as a default, and they recommend that. Now, if we go to Chromium, it's not like recommended, it's not the default things, but they say to use it. They recommend that, the way of using that one. And the reason for that is is like the confusion here is like for me when I try to move from C to C++, I had this idea that in order to initialize something to 0, I use this syntax. I used to use this syntax. So I use that in C++. Well, these two languages are different, right? They're not the same, they act differently, and they don't behave the same way. So this one on the blue doesn't act as the one in the in C. It's not the same the one in the C++ one, which is in the red. So basically, this syntax means the first element of the object gets initialized to that specific value. So they can select like different type of like initialization things, and you should learn those ones. And the documentation is quite heavy in that one. But the main idea is like if you like to have this kind of like 0 initialization thing, you need to use it like without any value inside. And this one's gonna give you like 0 value initialization. But let's have a look at this like at the assembly level, shall we? Now, if you take this another example like this one, the foobar, the same example, right? But this time I use like 41, hex 41. If we think of it, what kind of like elements or what kind of like initialization we will have. So we have 3, like a plus something from like the first index of buffer. What could be the return value in this one? Who can? Do you have any idea how? What would be the value? Would it be 3? Raise your hand if it's 3. All right. Okay. Who said something else? Yes. So basically, we used like this value. We use 41, which is like 65. It's gonna be 65 plus 3. That's the first value. Does C and C++ have type, string type? That's a question for you guys. Anyone can answer that? Who believes that C and C++ has like string type?
I believe C++ uses arrays or something.
All right, that's a good one. Yeah. How about C++? Does he have like C type, string type? Okay. Okay, that's a good one. That's a library, but it's not like it's a default library for C++, but it's not really kind of sort of thing. And we're gonna cover this one. And concerning the array, that's correct indeed. So basically, a pointer array, they're kind of like similar, but not like 100%. So C and C++ don't have like a primitive for strings. They have like the concept of using a pointer of a type of char, what could be anything really. So we can see here like the string hola, and we can see like in memory the layout, how it looks like. It ends by like a null terminator, and that's what, and they use that as a way how to determine a string. That's how it is. They don't have something else. This is more about legacy. Even like C++ have like certain things, and if you look at the APIs that you can use that, they all look for that null terminated string. It's not like, you know, it doesn't excel, it doesn't like scale easily, like when dealing with strings. It's very prone to error. So we don't have like really a type, but they're like in C++, they came up like with the standards to create like several types, right? So this is some of the types that we have in the library. As to like string, you know, several types, and those one are kind of still compatible with the C string. And the reason for that, at the end of the day, is like if we are interacting like with an OS, it's always gonna use the C ABI. And the C ABI is more portable and like known. Now, in C and C++, we have like several other forms of strings. Like in the project, like Qt, I would call it, they use their own kind of like string type. We have like some other like Microsoft things as well. But the one that we're gonna discuss is like the Unicode string one. And that's the main important one for our case because it's used like in the kernel. Now, I just want to say something as well. It's not gonna be C or C++. Even Rust have this issue of like having several types of string. We still didn't manage to fix the problem of having like a proper type of string. That's it's something that needs to be done, but yeah. So I just pick two types that I'm gonna discuss today. So the B basic string, B stands for basics, and string, and the Unicode string. And the reason why, well, basic string is used mostly with COM. We're not gonna use it because like the DLS they use that like comes like really late. But I want to use the example on how it's defined. Microsoft defined it as like a pointer, the way we see it earlier, right? But it's prefixed with the number of characters that, of bytes, sorry, not characters, but number of bytes. And they use like specifically some APIs that does the work for you. Although you can create like a bstring, basic string, and compile it like as a normal wide string, and it compiles, but it's gonna create error later on anyway, because like when you use the API, they would try to look at the format, which is the bytes prefixing like the string, and they still use like the null terminator. Now for the Unicode string is the main important one because it's widely used in the on Windows kernel. You're gonna see it everywhere. So it has like two fields, like the length and the max length and the pointer to the string, right? Now, if you've seen some libraries in C, they kind of like mimic this one. They name it slice string or whatever name they will always use this kind of type, length plus capacity. Max length could be capacity, and the buffer. Same principles, really. Now, the issue with this one, so when we deal with like non-optic kind of like, you know, objects, so you know the definition of the class of the object, what you're gonna do, you can end up like creating it manually. Some of the code base, you can see people try to create like a white string like the one that I said here, like incorrect. You can create it manually, but if you don't know what's going on, like what field is, you can make like silly mistake. In this case, for instance, which I always happen to me, although I kind of like been dealing with Unicode string for quite a while, but I still make the mistake, is the length is not really the number of characters, but the bytes. And since we're dealing with white char, and the encoding in Windows here is gonna be, the white char is 2 bytes, so basically the size of a white char. So you're gonna have like the characters multiplying by 2, and you get the number of bytes. And that's one of the main issues, but the real issue that happens to me is like I'm in the kernel, I'm having like a Unicode string, but then I wanted to do something very easily, check like some operation on the string. I use this this API. Basically, it looks if there is a string, you know, like contains something on that string. Now, does this code have like any issue for you? Raise your hand if you think that there is something dodgy with the code. Nobody? All right. So the thing with this one is when you receive like the Unicode string, there is like in the documentation for Microsoft, it's not guaranteed to have like a null terminator. So basically, if you use any APIs, C APIs, sometimes you can fail. And you will read like some garbage in the memory, and that eventually to get some you know, null terminator, but you won't have like the proper value that you want. So instead of using like something only for the string pointers, or use like the appropriate APIs meant for that. Any thing RTL, Unicode, string operation, use that instead. Or if you kind of like need really to use that raw buffer, what you can do is use like rely on the length and copy that length exactly, but be careful to not have like, you know, some you know, calculation error that you can end up with bounds errors. So that's the one about the C thing. So in conclusion, for me, like C, it's you know, strings, dealing with strings in C or C++ really, when you're not using the standards, it's very difficult. We need to really be careful and act like carefully in that regards. Now we're gonna jump into like another topic, which is the object lifetime thing here. So basically, that's the way, the general idea. Like we acquire like a storage, we construct it, and then we use it. At the end, it gets destroyed, and then remove that all. That's the general idea. We can see it here. It's a function here. So that the object of type t, whatever. It starts here and ends here. Imagine that like you're in a function, right? So you can use it here, and by the end of the scope, it gets destroyed. To illustrate the idea of like the lifetime here, it's this is a good example that I came up with, is to illustrate the idea of having like, imagine that in a function, right? And you have a buffer. You allocate a buffer. This one is on the stack, the first one. And then we say, okay, we ask C++, the new operator, to use the buffer as the allocation instead like of creating something in the heap, use this one instead. And then we call like here, like explicitly, we are calling like the destructor. Now imagine we don't call the destructor, we return the p variable there in the function. What would happen? We would have like a dangling pointer to an unknown, to a garbage, right? And even if you compile this one without any kind of like specific flags, you won't have any errors. So we're gonna talk about like flags and parameters that we can use. Now, from the object lifetime perspective, there are several types, right? The automatic one is the one that you create, like in a, as in stack variable, like the I for index kind of sorts of things. Statics one are like globally like lifetime. Thread local, this is interesting. We're gonna discuss that later as well. Dynamic is mostly like the heap one. You're most kind of familiar with like use FC3 kind of sort of bug. Mostly Terraform dynamic one, not traced. And temporary one, which is mostly for about like the short life of the object. And we can see here some example, right? This is a local variable, stays until the end of scope. This one, the static one, is global, like for the lifetime of that unit. And the thread one is per thread. If you create a new thread, you have a copy of that one. So you have like its own kind of like variable. Now, when it comes to the object lifetime, I think it's worth like mentioning the concept of like air value and left value kind of sort of thing. The way I remember this for me, R is like for rushing thing. I need something like very quickly just to borrow that so I can use it and then like dispose it. That's what the R value. It's temporary variable. Like the L value is anything that have like basically a variable name, an address kind of sort of thing. That's the way I picture that. So those are for the expression, and we're gonna see some like a case in that one that could be tricky. And the lifetime, obviously, is the life of the object, as we discussed earlier. So let's have a look at this piece of code. We have only 2 lines of code here. Now remember, I was like saying earlier that we have some restrictions. I'm using a C++ standard here to illustrate the mistake that I've made. On this environment, I'm not using any standards at all. I was kind of rewriting everything, and we're gonna discuss that later. But raise your hand if do you believe this contains some bug? All right. So I guess the rest is not. There's no bug. Okay. Cool. Well, surprisingly, this is 2 lines of codes, but there is like several kind of bugs there, and we're gonna like go through them. All right. Now I highlighted it a bit. So now we have a P, right? And I highlight this C string. C string is basically return a row pointer, right? And I'm trying to print it. But look, guys, I did something good. I verified if the P exists, like the address, right? Then I used like the to verify if the first value is not null terminated, kind of like it's kind of valid string, right? And I bypass that, and then I check the length. If like there is like a valid length, like something more than but still, when I see the logs, it's empty. I mean, what the heck? I mean, if you look at it, you say like, am I getting crazy or something? Well, actually, if we look at it, like we're gonna break it down. So what it does, the code, right? So we're using this file system thing is like from C++ 17, yes? Like started from C++ 17. They added this kind of like namespace and library. It's quite neat. Make it like very easy to deal with file systems. So the first one calls like path. Now, path itself, there is an issue with that. It can create a heap allocation under the hood, and we try to avoid like heap. That's one thing. The remove file name, if you go a bit further, it calls it, then we call the C string here. Now, when you call this C string, one that returns basically a row pointer, there is something that we don't see. That's the C, right? Like we see, like that's the thing that you see on the code, right? But there is something behind it. If you look at the assembly later on, we see a deconstructor of path have been called right after calling C string. Basically, what's happening is like that object is not gonna survive. It's gonna deallocate right after the instruction of CSTR here. So after calling this, as you can see, we get the value in RX here. They do something that I move it here, like using the stack pointer there. Then they move that there, and then they call right away the deconstructor, which removes this object, the first one there in the blue. So basically what we're gonna have, after this call, basically that call, we will have like an EIX or something, having a dangling pointer. So the object didn't survive until then. So basically, all this one didn't survive. So the solution to that is make it like extend the lifetime of the object. What I did here is very simple, really. I just kind of like put it in an L value, right? L value. We have a name, we have address, we have an address. It's an L value, and then we can use it like safely. As a matter of fact, you can use it that here as well with empty. Right. So this code, that's the fix, but I end up not using it at all. Why? Because I didn't read the documentation. This file system things, by default, raise an exception if there is an error. And exceptions are not allowed in my environment. So basically something goes wrong, and the program is not getting stable. So I ended up, but you can use like a return code in that. Instead of using this at all, I ended up like rewriting things in kind of C way. Now, I'm gonna move to another topic, which is like synchronization bugs. Okay, so synchronization bug is one of the most difficult components in programming. If anyone says otherwise, I would say he's a fraud, literally. So don't trust that guy if somebody says that. As a matter of fact, I don't know if you heard like Chronicles from Ubuntu just released like a report of, they did some security audit for the rewriting things in Rust. And interestingly, the bugs, most of them, were race conditions bugs, synchronization bugs. And yeah, so that's the most difficult bits. Okay, now I will give you like the scenario that I had. As I told you, we have the agent. It runs like super early during the creation of the process. But as strict, I cannot use like other APIs, like the Atomic one and some stud mutex, whatever. Although to be fair, you know, the standard of C++, you can use like, they can use like certain features, like the interlock internally, but if you, it depends on the size of the object you're trying to kind of use the mutex unlock of that. That's a side note, basically. But since it's not predictable, I will avoid using that. In that kind of sort of environment, we need to predict, we need to know what's going on under the hood. So the solution that I end up like using is using the interlock APIs. Basically, there are like CPUs instructions, like assembly instructions that we're gonna look at them. But this is one of the cases where I used the APIs, but I didn't use them properly, so I end up doing something wrong. And we will discuss this in a bit. So I use this model of like, you know, atomic things. As you, does anyone see some issue with this code, by the way? If you look at it at first glance. Anyone sees some issue with this code here? All right. That's a good, yeah, kinda, yeah. Yeah, basically in the code here, I think I kind of highlighted it here, is basically we're looking at the variable there. By the time we get into this one, things could have changed. Like there's loads of things that can go wrong. So we have two threads trying to read, write on that, like, you know, variable. they can read the same value, try to update it all together. So I end up using like the proper APIs, but I didn't use them properly. So I end up like still having the same issue kind of sort of thing, right? So we need to fix that. And surprisingly, I was looking at that, there is like this compare and swap thing. The compare and swap things kind of solve it. It does solve it actually, because we'll see this under the hood in a second. But if we just like I want to get back to the previous one here, you can picture this one like in several instructions. I can see compare, then jump after, if not zero, something like that. And then you need to copy something else and return things. So basically you will have like several instructions there. And well, in this case here, we can have like an old value we expected. If it doesn't like much, with this one, we have the enter, compare, exchange, right? Doesn't mean this under the hood does like only one single operation. It checks for something and like assign it to something else in one single instruction. Now, bear with me. Those APIs really, the size of the object they're gonna use on them matters, right? They basically is not something big. You're not gonna use them for, like for big objects or structures like that. Some elements of that, right? Now, if you go back here, the most that's the instructions under the hood, and that's how it works. It's compare something. If it doesn't match, like it returns something. But the most important keyword here is lock, right? The key lock things guarantees that oh, he sends a signal. The CPU should send signal, say, oh, you look, I'm like looking at this one. I'm using it, kind of sort of thing. Come back later, kind of sort of thing. That's my analogy in that one. Please don't, take it with a grain of salt on the way I'm phrasing it. But so that's the solution that I had. So instead of like using like mutex, again, like the reason why I didn't use those things, just to mention again, is like I don't want to have like any deadlock with the Windows loader. When try to load something, is very sensitive. If anything goes wrong at that period of time, deadlocks, and you will have like a very weird message and behavior kind of sort of thing. Now, after fixing the issue, I came to another issue this time. This time is not about like who's like racing who and who's gets like will change the value and here and that. But this time is I'm having like a memory bug, but kind of using the same principles that I used earlier. The only thing that I changed though is using thread local storage, the one that we talked about earlier, the local thread. One use that under the hood. Now, so basically this one, the way I see it is like there's two types of them. There's the dynamic one and the static one. Basically, it is an array, an object, an array with an index kind of sort of thing, and you go there and allocate it for you. So basically, every time you run a thread, and you have a copy for yourself for that specific per thread, that value. That's the way it works. It should be fine. Now, the way we use it, if you're using C++, you can have it like that, like the thread local. There is another expression for C, especially for it's a delc spec, and you put it like a thread between parentheses. But if you look at this this code here, right, we're using static TLS here. So we allocating a variable called isLoader, global isLoader, right? Is a type of thread local. So basically every thread has a copy of that, and then use it. Like is local true. The way I use this function, this code here is like to flag if this code comes from like a loader or something like that. Now, is there an issue with this one? I see this one here, like a write. We have like a write operation over here. And for some reason, I get like a null pointer the referencing on that. And that's weird. And why is that though? Now the reason for that is I injected my agent like super early that even the TLS1 was not initialized. So I had this issue. So how to solve that though? I use like the TLS1 the static one, what you can do to fix that is very simple. If you look at this code now, let's have a look at this like first before we move there. This is the code, right? This is what it generates. It gives you an idea about what TLS is anyway. So we can see like we're accessing the tab, right? That's the thread environment block, and then it gets like the pointer of storage pointer, and then get the TLS index. This one get generated during the linking time, right? So those are not like dynamic, so they should be there. And then there is like another plus index value. This one is like defined depending on the variable that you get. So if we use this principle, I can basically what I can do, I can access the tab, right? I can do it manually and try to do that. The only issue would be how to access this value here. The index for that specific variable. How can I link them together? Well, it turns out I don't need to do that, although it's like technically feasible in that sense. We can use like the APIs that they offer us. We can use the dynamic TLS bits. And this one you can allocate the things, and you can make the checks manually, and you won't face any issue about like null dereferencing. So basically here we can say the abstraction that we had with the TLS, static TLS, put us in a position where we don't control things. Now, in our area of work and the way we write those tools, we need to have like full control. In order to do that, Microsoft offers, like for that one, we can use those APIs. So use those APIs when you want to control. So you cannot face like the things that we face. And this one happened like, I mean, it's really convenient to be honest. Like you just use thread local and you call the function kind of sort of thing. But under the hood, like we see that things going on. But like there is some instances like the one that we, like the one in the red here, that's the one that I run into, kind of sort of thing. So, so we should really kind of like be careful when using something like very, how would you call it? Like something that we don't control, especially on that environment. Now, let's move to the Windows 32-bits kind of platform pitfalls in that regard. This is an issue that I faced with one of my agents, right? So my hook was working perfectly on 64-bit, like amazing. Everything was working perfect. I tried to test like my 32 bits, and suddenly I see a crash. But when I look at it, I kind of like that's the same logic, that's the same code. What's going on, right? What could be the error, right? I have looked at every kind of like side of that. Now my assumption was like when I looked at the code, like a C code of that, there is the same type, there is the same kind of like, you know, signature prototype kind of sort of thing, but there's something that I completely forgot. We're dealing with 32 bits, right? 32 bits or x86, they use like stack, right, to pass parameters and so on. And there is a contract for the API that we need to follow. And I didn't honor that. Obviously, you kind of see like some issues for that one. So basically, I kind of like provided something, and using the Windows like APIs, it should expect, they use like the ST standard call, and they, so the callee or the caller kind of do specific roles, like for the type of like the calling convention. Somebody needs to free it or like deal with that allocation. So since I didn't have that in mind, so something went wrong either like from the parameter passing or from the return value. In my case, it was the return value was like I have like the stack corrupted in that sense. So it was in the return value, not on the parameters. Now, if we look at the Windows like macros, so the STD call is the calling convention of Windows. Most APIs that we'll use on Windows is like this is the calling convention basically. That's like if you are on the user lane, you will see Win API, right? It's the equivalent for NT API, but here we're like with the new technology API, like at the NTDLL level. And this fixed the issue. So basically, I find that the thing, I fixed it, and it was like working perfectly. The crashes, like I spent several time on that, like trying to debug what's going on, like with the stack. Like I've been like on Win debugger, like trying to understand what's going on, and that was a silly mistake. Just like simply didn't honor like the contract, the API contract. Now we're moving to the most interesting thing, bit in my humble opinion in this one is Who agrees that modern compilers are smart? That's good. Right. And they are indeed. So basically, this is an example, one of like my hooks that I had. So notice like in the red, I have like this add DLL directory function, right? I call it several times, right? With different values, right? And this time I respected the call convention, right? It's still like in 64 bits, in 32 bits. We're still in 32 bits. But somehow it's been crashing. I didn't get it at first. But just for your information, you can you can rewrite the code there, like have it in list and do the for loop or anything like that. The compiler will still produce this piece of code, this assembly one. This is like the optimization level of that one. Does anyone notice something, any red flag in this code? Anyone? Raise your head if you see like a red flag. No? Nobody? All right. So let's have a look at it, right? So basically what we have here, we're on 32 bits, right? The compiler, what he did, super smart. He kind of like saved, not kind of, but he did. He saved the address of the APIs in USI, right, register, and then pass the string and call it again and again and again, right? Now, for me, this is like a very red flag, but I'm not saying it's not safe, but this is a red flag in sense. The compiler picked like a non-volatile register, meaning the value that you put there will stay there. So you're responsible of like saving that value and use it and then like put it back. Basically, that's the meaning behind that. And when I looked at the code, I was like, what the heck is going on? This is not safe. Why are you using ECI thing? So if somebody calls it, it's going to change the value, and that's maybe the reason of the crash, right? But no, I was wrong in that one, because as you can see on the green, right, we have like he saved it like properly. He saved it properly, so it's safe. Like the users here is safe, even though it's not non-volatile register, but it's still safe. So I was like, what's the issue then? It's safe. I've been debugging it. I even went like even further. I was like looking all the call of that Windows API there, like reverse engineer it and saying that the assembly and try to see if ECI is called or something like that. But you know, Microsoft is good at that, so they sanitize and they verify the code, so there's no way they leave something like that, right? So I didn't know how to fix that. What I was like, oh, since it's an optimization thing, let's say to the compiler, please don't optimize this piece of code, right? Just leave it as it is, right? And it did fix it. That's the temporary fix. But I was not satisfied with that. I was like, come on, what was the issue, right? There's something wrong. Am I like, did I find like an optimization bug in in the C++ Microsoft compiler? Maybe, maybe not, I don't know. We'll see. Turns out, no, that was not the case. The injection that I had like on my shell code was the issue of that. I was using those non-volatile, again, registers, and at some point I forgot to save them and get them, restore them properly. And this is one of the piece of code here that I'm using ASI and ADI, which are not like, again, they are not like, volatile, and that those one who caused the bug. It was not like a compiler bug from Microsoft. That was my mistake. And yeah, we getting into the end of this talk. This is the conclusions. I would say in this kind of environment, if you're dealing like in low-level aspect system programming, there is no room for assumptions at all. You need to understand what's going on under the hood, have more like, the context, what's going on. In assembly we trust, although I know I say that, but even then, like there's some cases where CPU act differently, so the assembly instructions doesn't act as used to, but at least we have that level more than the code that we have. Yes, again, C and C++ are two different languages. Please don't try to kind of act as they are the same and like do, the mistake that I made for the initialization part. Um, the running environment here matters a lot. Now, if you are in the user land, you won't face any of the issues that I kind of like showed here, demonstrated here about like the early initialization things. Those you won't see them at all. It's gonna work just fine. Even like using the standards, C++ standards will work just fine. Now, that's the main important thing for me. I think like abstraction is not really, doesn't bring too much like in this kind of work. And again, I picked C++ in this project. Why I moved from C to C++ to take advantage of like the C++ compiler features, right? I wanted to get, use that in my advantage. The way I wrote code was like more C-like. But if you try to follow this C++ way in certain things, that creates a level of abstractions. And the level of abstractions, this is the thing that I don't appreciate, I would say. As we saw earlier, like the lifetime bug there was a call to a deconstructor and we didn't know that. We illustrate that as well with the initialization bit, the order which one gets called first. There's several things that are not like straightforward. So abstraction is not necessarily good. Like in this low level aspects, the more transparent you are, the more easy it is to audit your code and you know what's going on under the hood. Use the code API for the code object. I'm referring to the C strings here. If you have a Unicode string, use the APIs made for that. Don't extract the buffer. I don't assume that there is a valid like null terminated C string there. As a matter of fact, I would say don't trust any input at all. Try to always bulletproof anything. Really, everything can happen, especially at that low level. Use address sanitizer. Although, to be fair, I just use like Microsoft's compiler, right? The original one, CL thing. There is the CLang CL, which has like very like address sanitizer works well there, but I don't have like a good kind of like experience with CLang CL in that regards. So basically, with the Microsoft one, the address sanitizer only have the address and thread options. If we use like, if I use the address one, I would have noticed the bug of the lifetime, right? Now there are like other things undefined, and I guess memory as well that you can use like on like GCC and Clang, but they are not like available for with the default Microsoft compiler. So just try to take advantage of like the address and thread one. They're quite useful. Use them during the cycle of dev. You will find loads of bugs, trust me. Synchronization programming is complex. I would say like treat that like really carefully, especially when you are like in the kernel. That's very, don't risk that. Timing matters a lot in sense of like, I had at some point to delay my injection just for the sake of like facing some weird initialization of kernel 32. On specific version of Windows 11, everything was working fine. On another version, I have like some weird crashes on certain processes. So I had to use delay kind of sort of thing. I don't like this approach. It's not like a really engineering, but it solved my problem for that one. So yeah. Respect the calling convention. Remember, if you're dealing with like 32 bits, there's several like calling convention. Make sure to respect that. Now I didn't, we don't have like ARM here. I didn't, so we're not covering this one. If you end up doing some, assembly programming, please make sure to, preserve the non-volatile registers. Goes in both ways, 32, 64-bit, doesn't matter really, just respect that. Although like the 64-bit one, yeah, you can get more loose, but even then, like you need to be careful. Do not blame the optimization too early. That's me. I thought that I found like, a compiler bug. Silly me, but yeah, it ended up I am the one who caused the bug. Treating 64-bit success. Well, as a matter of fact, if you have like multiple platforms, you need to test them all not only like rely on specific architecture. You never know. So they differ. There is a reason for that. And my last kind of like point would be fail, repeat, and succeed. That's the one that I only recommend for that one. And that would be all. Thank you for, and if you have any questions, please let me know.
Thanks, Taha. Really great talk, really interesting. Early on, when you were talking about the, I guess the initialization and order of them happening, is that language defined, or is it dependent on architecture and dependent on compiler? I can remember they were red and orange in your code example. Is it compiler and optimization dependent?
Which one? Like I'm trying to
keep going back.
Yeah, I'm trying to the initialization bits, right?
Yeah, the two initializers and the order. That
This one.
Yeah.
Oh, yeah.
Is
No, this is a defined behavior, by the way. Okay.
Defined.
Yeah, it's so basically when you put the assembly level that generates, it always starts with something that you can have like as a value, right? So there is no calling. So the second one, the constructor is a calling thing. So it's obviously it's gonna be called later. But in the standards of C++, the first thing that it looks for is like the constructor, an empty constructor. If it's there, that's the one that gets called first. So basically, what happens here is the assembly code gets generated there. But the buffer one gets generated to 41. We don't see that for the optimization here in that one. And then you get like overridden by the constructor. And if you go to the initialization on the documentation of CPP, they will tell you this kind of behavior. It's something they have kind of specific order conditions and that. I kind of like was like trying and seeing how it works, basically. That's how I kind of like end up figuring it out, to be honest. But yeah, thanks.
Thanks.
Thank you, great talk. The example you gave about the length of the Unicode string, for example, it gives you the number of bytes, not the number of characters. Is there a workaround if you're dealing with non-ASCII characters?
This one, right? You're referring to
Yes,
this
yes.
a workaround for non-ASCII
Yes.
characters? Well, this one is like a white string, right? The Unicode uses like white string. Well, I would say use like the APIs to construct like that Unicode string instead like of creating it manually. That will give you like the right kind of like value for that.
Okay.
But yeah, that's I think that's the important thing. Always use the API related to that. Don't create it like manually. I think yeah, that's the point there.
Okay.
But I'm not sure if I get like the question properly. I mean, am I answering your question?
Yes, yeah. I'm just, for example, because you mentioned it gives you the number of bytes rather than the number of characters.
Oh yeah, like so basically what's going on here, if we go through it, so Unicode string is based like on white string, right? And and white string like on coding in Windows, like it's 2 bytes. One character is 2 bytes.
All right.
So basically, if you have hola here, it's like 4. Yeah, 4. You know, you multiply by 2 is 8. Plus, you need to calculate. You need to add like the null terminator there yourself. So you will have like 9 bytes in total.
Okay.
But you need to make the calculation yourself. But yeah.
Yeah. Thanks. Thank you.
No worries.
Any other questions?
Yeah.
No. Cool. That will be all then.
All right. Thank you.
Thanks.